For number 33, we have a 24 kilogram light fixture. It's hanging from a uniform 3.5 kilogram beam that is 1.6 meters long. So here's our light fixture here. Okay, and here's our beam. Or sorry, that's our pole. Here's our beam. And the beam is 1.6 meters long, so I've labeled it as R. And we have, this is a 3.5 kilogram. So little mg is the force that's causing, and I'm calling little m is the 3.5 kilograms. And big M is from our light fixture, which is 24 kilograms. Okay, so our R value, as I said, is 1.6. And because it's a uniform beam, the R value for the center of mass for the little m is 0.8 meters, so half of 1.6 meters. And I've chosen my fulcrum to be right here. And the questions are, find the tension in the cable. So you can see I've drawn some vector and vector components. So we have the tension right here, and then the y and the x components. And then the second part says, what is the force exerted on the beam by the pole? So here's our pole. So there's some force, okay, by the wall that looks like this. Okay, and I've drawn it here. Here's my force by the wall, and then it has a y and an x component. So you see down here I've drawn my two triangles for later on. Here's my tension force, and it's at an angle of 33 degrees. And it has a y and an x component. And here's my wall force, and it has a y and an x component. I don't know anything about the angle or anything else about that at all. So what am I going to have to do? I'm going to have to apply all three equations here for static equilibrium. So the first one is the sum of the forces in the x direction is going to be 0. So the forces that I have in the x direction are just the force of the wall, and in the x direction, so Fwx, and we'll say that's in the positive direction, and then we have the force in the x direction from tension, we'll say that's in the negative direction. And those equal 0, so from that you can just see that they have the same magnitude. They're the same size force, just in opposite directions, okay? So then in our second equation, the sum of the forces in the y direction have to be 0. Okay, so from that, the y direction, we have the force of tension in the y, the force of the wall in the y, and then the two weights, the one from the center of mass and the one from the light fixture hanging on the end. So I have the force of tension in the y direction plus the force of the wall in the y direction minus little mg minus big mg equals 0. Okay, and then lastly, I have my sum of my torques has to be 0. So all my counterclockwise torques are going to be positive. The only counterclockwise torque, because of where I've chosen my fulcrum to be right here, so the only counterclockwise torque is coming from tension. So I'm going to have the force of tension in the y direction multiplied by R is my counterclockwise torque. And then I'm going to subtract the two torques created by the mass. So the one is from the center of mass of the pole of the pipe or the beam. So that's little mg times R over 2 minus big mg times R equals 0. So that's all of our torques. So from this equation that I just got here, I can solve for Fty straight out. So I'm going to have G times little m R over 2 plus big M R, and all of that is going to be divided by R. Okay. That all, oh, no, I didn't have to do that, sorry. And you can see if I divide everything by R, then these R's are all going to cancel. So this is just 9.81 meters per second squared times little m over 2, so 3.5 kilograms over 2, plus big M, which is 24 kilograms. And I get the force of tension in the y direction to be 253 newtons. So I've gotten this here. This is 253 newtons. Okay, so if I know that and I know my angle here, then it's not hard for me to apply a little bit of trigonometry, and I can see that the force of tension in the x direction is just going to be the force of tension in the y divided by the tan of the angle, which is 33 degrees. So the force of tension in the x direction is 253 newtons over tan of 33. And from that, force of tension in the x is 390 newtons. Okay, and because of our first equation way up here, this one right here, we see that the force of tension in the x is the same as the force of the wall in the x. So I can go back down and I can actually say that this is also the force of the wall in the x. So I've just found this one right here, right? And that's 390 newtons, sorry, 390 newtons. So I've already got that. So now all I need to find is this right here, the force of the wall in the y direction. And I'm going to use this equation here because I know everything else in that equation. So I can say the force of the wall in the y direction is just little mg plus big mg minus the force of tension in the y. Okay, so the force of the wall in the y is g times m plus big M minus the force of tension in the y. Let's scroll down a little bit. So that gives me 9.81 meters per second squared times 3.5 kilograms plus 24 kilograms minus the force of tension in the y, which was 253 newtons. And that gives me the force, the wall, in the y direction. Which is a 16.8 newtons. All right, so I have this now. This is 16.8 newtons. All right, so if I want to describe my vectors in terms of magnitude and direction, first thing I can do is I can describe them in component form. So the force of tension, I could say the x is in the negative direction, so I could say it's negative 390 newtons. 390 newtons I hat, so that just means the unit vector in the x direction, plus the 253 newton y direction, and I call that times the unit vector in the y direction, which is j hat. And then I can just say, okay, well, what's the length of that? I can just use Pythagoras. And it's just going to be 390 newtons squared plus 253 newtons squared, and take the square root of all of that. So that gives me the magnitude of the tension, which would be 465 newtons. And I can quickly figure out the angle that I care about. Actually, for tension, I don't even need to figure out the angle because it's told to me right off the bat. It said it's 33 degrees. So I can say that the tension vector is just 465 newtons, and it's west 33 degrees north. Okay, and then I can do some more trig just for my wall vector. So I know it's 390 in the x newtons and 16.8 in the y. So I could say the force of the wall in component form, they're both going to be positive, so 390 newtons I hat plus 16.8 newtons j hat. And if I want to find the magnitude and direction from those two components, again, I just apply Pythagoras. So 390 newtons squared plus 16.8 newtons squared. Take the square root of that whole thing. And and I get, it's 390 newtons because the 390 dwarfs everything compared to the 16.8. And theta is just going to be the arctan of 16.8 divided by 390. My newtons cancel. And I get something like 2.5 degrees. So I could write my force vector from the wall is 390 newtons east, 2.5 degrees north. So there's my wall vector, there's my tension vector.